Imagine a guy, we'll call him Doug, sitting in a tiny little boat, bobbing directly over the Mariana Trench. That is literally the absolute deepest point on planet Earth. And he's just sitting there, holding a 7-kilogram bowling ball right over the side of the boat. Okay, let's dive into this. Doug wants to know exactly how long it would take for his bowling ball to hit the bottom of the trench. But before we can actually calculate the timing of this epic drop, we've got to pause and address a pretty surprising fundamental fact about the object Doug is holding in his hands.
Section 1, the bowling ball buoyancy myth, and why the phrase sank like a bowling ball is actually completely wrong.
Right, so to understand what happens next, we have to look at the physics of displacement and honestly bust a massive misconception. If you've ever used the popular simile, sank like a bowling ball, well, you're going to want to rethink your metaphors. The magic number here is 12.13 pounds, or about 5.5 kilograms. See, because standard bowling balls are all the exact same physical size regardless of their weight, every single standard bowling ball displaces the exact same amount of seawater. And that displaced seawater weighs exactly 12.13 pounds. The law of buoyancy tells us that only objects weighing more than the water they displace will actually sink. So literally only bowling balls heavier than 12.13 pounds will go down. And this brilliantly illustrates the divide. If you look at the left side, the average ball you just casually pull off the rack at your local bowling alley weighs about 10.5 pounds. That means for most people, the average bowling ball they pick up in their lives will happily float in the ocean. But over on the right side, we have Doug's specific ball. He's holding a 7-kilogram or 15.5-pound ball. That easily blows past our 12.13-pound threshold, making it plenty heavy enough to sink like a stone. Moving into Section 2, sinking in the Mariana Trench. Let's look at the physics of the drop. So as Doug plunges his specific 15.5-pound heavy hitter into this 11-kilometer deep trench, mechanical forces actively battle each other. As the ball falls, its speed is dictated by two main things. You've got the drag equation pushing back up against it as it cuts through the water, and the ball's apparent weight pulling it down. What's really interesting about this is how quickly these competing variables balance out, locking the ball into a constant, steady speed downward. And that constant speed, its terminal velocity, is roughly 1.3 meters per second. That is exactly how fast Doug's heavy 7-kilogram ball plunges through the dark, freezing waters of the trench. Which brings us to the ultimate answer to Doug's question. Descending 11 kilometers at a steady terminal velocity of 1.3 meters per second means the total descent time to the bottom of the Mariana Trench is about 2 hours and 20 plunge into the absolute abyss. But keep in mind, that 2-hour and 20-minute time is entirely dependent on the specific 15.5-pound weight Doug used. If Doug had used a 13-pound ball instead, well, it would be much closer to being neutrally buoyant in seawater. Because it barely overcomes the drag, that slightly lighter ball would take a painstakingly long 4.5 hours to sink to the exact same spot. Section 3. Heavy metals speedrun the abyss. Let's talk about extreme density drops. So what if we went in the other direction? What if we swapped the ball's material to something insanely dense? Let's take this thought experiment to the absolute extreme to really see ocean physics at work. Look at how dramatically the descent times shrink here. A standard-sized bowling ball made of solid iron, that reaches the bottom in just half an hour. Lead, down in 24 minutes. And then we have solid osmium. Osmium is the heaviest naturally occurring element. A standard-sized bowling ball made of osmium would weigh over 250 pounds, and it would rocket down to the trench floor in just 16 minutes. And yeah, for the record, a solid gold ball would be incredibly fast too, making it down in about 18 minutes. But, as you'd guess, it would also weigh more than the average bowler and cost over $10 million. I am really not sure why you'd be chucking a $10 million chunk of gold into the ocean, but hey, if you do, expect an 18-minute drop. Let's move to and see how this builds in Section 4, the epic Trans-Pacific Drift, following the path of the floater. Let's look at an alternate timeline. What if, instead of the 7-kilogram sinker, Doug brought that average 10.5-pound bowling ball from the local alley? You know, the one that floats. Since it never actually reaches the bottom, it becomes completely at the mercy of the ocean currents. To figure out where it goes, we can track it using an amazing data model called the Plastic Adrift Ocean Tracking Tool. This maps out exactly where a floating object starting over the Mariana Trench will travel over the coming years. Just follow this incredible timeline. In the first month, our buoyant bowling ball drifts west past the Philippines. By year 1, it's heading north along the coast of China. Around year 2, it takes a sharp right turn at Japan, heading out across the vast open Pacific. And then, 3.5 years later, it finally approaches the coast of California. It might get swept up into the Great Pacific Garbage Patch, but it could very well just wash right up on shore.
Which brings us to Section 5, the ultimate improbable strike, 3.5 years later in Los Angeles.
Let's merge our floating timeline and Doug's story right there on the west coast of the United States. Imagine Doug puts this wildly elaborate plan into motion. Step 1. Right after dropping the floating ball, Doug sails his boat from the Mariana Islands all the way to Los Angeles. Step 2. He finds a nice sheltered cove and sets up 10 carefully weighted bowling pins just below the surface of the water. Step 3. He simply sits and waits for 3.5 years. It leaves us with this final provocative thought. Could the single most mathematically improbable strike of all time actually happen? Well, according to the data, there is a tiny, tiny, tiny chance that he could pull it off. It's an amazing testament to the sheer scale of ocean physics, from the relentless math of terminal velocity pulling a 7-kilogram weight to the ocean floor, to the incredible trans-Pacific journey of a floating sphere. Next time you pick up a bowling ball, just ask yourself, is this a sinker or a floater? Thank you so much for checking out this explainer, and keep questioning the science around you.